Okay, so in this section, we're in 4.7 now. We're talking about change of basis. And one thing I want to talk about before we get started is something I meant to talk about back when we first introduced the concept of a basis and coordinates relative to a basis. And that's the idea of an ordered basis. So if we're going to think of bases for vector spaces as coordinate systems, which is in class how I sort of introduced the idea, it's crucial that we think of these basis vectors as being in a specific order. So here, and I'm going to shoot past this paragraph and just talk about this. I'm in a vector space V. It's n-dimensional, and here's a basis for that vector space, V1 through Vn. Okay. The order that I write these in this basis is going to matter for what we do in this section. Normally in just any old set, if you rearrange the elements of a set, we don't consider that to be a different set than what you started with. But for the purpose of an ordered basis, we're going to consider the order to be important. So if I swapped V1 and V2 here, even though it's the same basis, I would count that as a different ordered basis. And the reason that matters is because the ordering determines what each coordinate in a, here's an example, what each coordinate in a coordinate vector corresponds to, okay? So I'll use that term here and there when I'm talking about this stuff. Ordered basis just means that these vectors are in a prescribed order. So for this discussion, we're in a vector space V, and we're going to talk about two bases for this vector space V. There's a B, which has these vectors, B prime, which has these vectors in it, and I'm going to let little v just be any arbitrary vector that lives in V. Okay, now the idea here is basically transitioning from one basis to another. It's the same idea as converting from one coordinate system to another, which is something you've already encountered in previous classes. How does that work in vector spaces? Well, let's suppose for a second that this guy V here, that we've already determined what its coordinate vector relative to B is, this B right here. So we've done the work to find this. It's an n by 1 vector. These scalars correspond to what I would be multiplying each vector here by to give me a linear combination equal to V. Okay, let's move that up a little bit. Now, if this coordinate vector relative to B looks like this, then that means V can be written as a linear combination that looks like this. These C's times these V's, like we just said. In addition to that, what I'm going to do is take each individual coordinate vector from B and express it also as a, sorry, I think I call these coordinate vectors. Each individual vector, V1 through Vn, I'm going to express each one of these as a coordinate vector relative to the other basis, B prime. Okay? That's possible because, again, if this is a basis, then that means it spans V, which means every vector in V, including these, can be written as linear combinations of these. I don't know what that would look like because I'm keeping things general here. So let's just say that these are the coordinate vectors for all the V1 through Vn relative to B prime. Okay, and if you notice the notation I'm using for my entries, A11, A21, and so on and so forth, they look like entries in a matrix. That's intentional. We'll see why those are being written the way they are in a moment. Okay. So now, using this, the fact that V can be written as this linear combination right here, notice that the V1, V2 through Vn, because we have coordinate vectors for each one of those relative to B prime, these give me a way of expanding each of these vectors as linear combinations of the vectors in B prime. So I'm going to take this linear combination and kind of blow up each of the V1, V2, Vn as linear combinations of all these V primes now. And that makes this linear combination for V really complicated looking. But if we think about what this is, I've taken what was originally expressed in terms of V's and turned it into an expression that's now given in terms of V primes. Although to make it a little more useful for our purposes, we have to rearrange a lot of these terms. So notice if I were to distribute the C1, C2, all of those C's into these parentheses, and then because all of this is addition right here, if I just combined like terms, so if I combine the V1 primes, the V2 primes, and so on all the way down, I can see that my V1 prime is going to have as its coefficient C1A11 plus C2A12 plus so on and so forth. That's all right here, okay? And if I do that for all of the other terms, as I combine them, what this does is it expresses V now as a linear combination of the V primes. That is a linear combination of the vectors in my new basis B prime up here, okay? So that tells me how to write V as a coordinate vector relative to that other basis B prime. Again, these scalars, these are not linear combinations in the parentheses. These are all scalars here. Those become the entries of my coordinate vector, okay? Now, each line in this coordinate vector is just a single scalar, but expressed as a big sum of several products. That can be written more efficiently as a product of these two matrices. Notice if I wrote it this way, you can see pretty clearly that this column is going to multiply to each row in this matrix, giving me this, right? However, this column matrix is exactly what we came up with up here. That's the coordinate vector V relative to B. So, in order to convert a column matrix, or sorry, not a column matrix, a coordinate vector for this vector V relative to B, which we're going to be calling an old basis, into the coordinate vector for V relative to B prime, the new basis, it basically reduces down to multiplying this coordinate vector by a specific matrix. That matrix we call a transition matrix. And if you think about where the columns of this matrix came from, the columns of this matrix are just these column vectors right here, okay? So that gives us a way of coming up with this transition matrix. Let's go ahead and go on to the next page. All right. So, again, that matrix that we just referred to, we call that a transition matrix, and this is the notation we use for it. It's P, and then as a subscript, B with an arrow pointing to B prime. And again, B I'm going to be referring to as the old basis, B prime the new basis. This is the new basis, meaning the one that we want to convert to, okay? So using that notation, the matrix multiplication that we saw on the previous page is more concisely written this way. Notice if I want to convert to a coordinate vector in B relative to B prime, I'm starting with a coordinate vector relative to B multiplied by the transition matrix that carries coordinate vectors from B into B prime, and that does it for me, okay? And again, to write in kind of more compact notation, that transition matrix can be written as a partitioned matrix. Remember, each of these represent a column, where I took each of my vectors in my old basis and expressed them as coordinate vectors in my new basis, creating those columns, okay? If I needed to do this the other way around, if I wanted to express or find a transition matrix going from the new basis back into the old basis again, then I essentially do the opposite of this. I take the vectors v1 prime, v2 prime, I take all of the vectors from my new basis, and then I express them as coordinate vectors relative to the old basis. Load them into this transition matrix as columns, and that becomes my transition matrix. So let's do an example where we're computing some of these and using it to convert from a vector from one basis to another. So here we're going to determine the transition matrix from B to B prime as well as the transition matrix from B prime to B, where B and B prime are both bases for the vector space R2, okay? And those bases are shown here. So again, starting with B, the transition matrix from B to B prime. Remember, what you want to do is take the each basis vector and express it as a coordinate vector relative to the new basis. So starting with the first vector here, this is for part A. Our first vector looks like 1, 0. We're expressing this as a coordinate vector relative to B prime is just a matter of finding what constants I would use. So 0, 3, 1, C1 times 0, 3 plus C2 times negative 1, 1. What constants I would need to multiply each of these vectors by in a linear combination to make this, right? So if I distribute the C1 and the C2 in and then add everything up to get a single vector, I should see a negative C2 here, 3C1 plus C2 there. Okay. Now, more complicated examples, determining the C1 and C2, or however many of those constants we need, can, boil down to solving a big system of equations. But in this case, it's pretty easy just to solve by inspection. Notice 1 is equal to negative C2. So that implies that C2 is equal to negative 1. Then if I substitute a negative 1 in for the C2 here, and then determine what should C1 be so that all this turns into just 0, that's easy enough. That should just be 1/3. So C1 is equal to 1/3. What does that mean? Well, for this first vector, vector 1, 0, if I want to express it as a coordinate vector relative to B prime, I just use C1 and C2. It's 1/3, negative 1. Okay? I do this again for the second vector in that set, in that basis. So 0, 1. I rewrite that. I'll use different letters for my constants here. D1 times 0, 3 plus D2 times negative 1, 1, which is the same thing as negative D2, 3D1 plus D2. And again, this time I'm setting these components equal to these components. So 0 would be equal to D2. Pretty clear. We can see that. So I'm going to say D2 equals 0. And then if I plug a 0 in for the D2 here, I have 3D1 equals 1. So that D1, like C1, is equal to 1/3. That means this basis vector 0, 1 expressed as a coordinate vector relative to B prime is going to look like 0, messed that up, 1/3, 0, or that. Okay, these vectors in this order, remember the order matters, are going to be introduced as columns in this matrix, this transition matrix that we're looking for. So my transition matrix, P from B to B prime, is going to look like this column, 1/3, negative 1, followed by this column, 1/3, 0. Okay? If I wanted to do this in reverse, I would do the same thing, just using this as my old basis and this as my new basis. So I would write 0, 3 is a linear combination of these two vectors. Something interesting happens there. You notice this basis is the standard basis for R2. When we're converting to the standard basis for a vector space like Rn, the transition matrix is actually very, very predictable. I'm going to let you determine why this happens, but if I want to express, for example, 0, 3, relative to B, where B is now the standard basis for R2, it turns out that this is just equal to 0, 3. It looks exactly like our original, let me scroll that up a little bit. It looks exactly like the original vector. So that's great. That only works when we're converting to the standard basis for R2 or Rn, or it works for standard bases for other vector spaces as well. If this is true all the time, then I can do the same thing for the other vector in B prime. So negative 1, 1 is what that vector was. If I express that as a coordinate vector relative to B, that's going to look like the column vector negative 1, 1. So this means that my transition matrix from B prime to B just looks like 0, 3, negative 1, 1. Okay? You can go through the steps of doing this the longer way if you want to, just to confirm that the results I'm getting are correct. But it's worth doing that on your own just to sort of see that. That's part A. Now part B, take a look at part B. We're asked to take this vector, 3, negative 4, and express it as a coordinate vector relative to B prime. And I could do that the old-fashioned way, you know, express it as a linear combination to find those scalars. But instead what I'm going to do is use the fact that the vector 3, negative 4 relative to B, again, B is the standard basis, just looks like this, looks like itself, right, as a column vector. And then I'm going to use the fact that I've already found a transition matrix that takes vectors relative to B and turns them into vectors relative to B prime. So this becomes a matrix multiplication problem. If I want 3, negative 4, but relative to B prime, then what I'm doing is I'm multiplying this transition matrix on the right by this column vector. So this is going to look like 1/3, 1/3, negative 1, 0, times 3, negative 4. And if you carry out that matrix multiplication, what you end up with is negative 1/3, negative 3. Okay? So these are the things that we were asked to look for. There's both transition matrices, and here is the vector that we were asked to find relative to B prime.